we know what we're doing here, you know, but we're also going to extend this a little bit further and start talking about unit circle concepts if we get that far. I'm in no rush. Here's why. This section in particular is huge to your overall understanding of the unit circle and how we're going to use the 30, 60, 90 triangles and the 45, 45, 90 triangles to make our way through all the trig that we need to do. And if you look at your notes for 4-3, you should be looking back there going, really? We're going to take 3 days? Yeah, we are. We're going to take 3 days. We're going to make sure that you have what you need. And that said, please don't sit and work on the homework, because chances are pretty good we're not going to get through everything we need to get through for you to do the whole assignment anyway, you know? Because this is such an important background section, make sure that if, as we're going through this, anything doesn't make sense to you, that you ask. And one of the biggest roadblocks right now is going to be pi. It's going to be a big roadblock because most of what we do in trig has to do with radian measures. So we have to start, like I mentioned yesterday, thinking, okay, normally this is 180 degrees to me, but now if they give me something in pi, how could I reason? 180 is pi, how many of these will fit in that straight angle? And use that to think of our fractions for radians. So like it says, it's trig extended. We're going to start extending to the circular functions. We want to be able to find the trig functions of any angle. Find trigonometry functions for real numbers and describe the periodicity of trigonometric functions. So there's a word you haven't had before. It has to do with, well, you know what, just a that's the pattern on Charlie Brown's shirt, right there. So periodicity means how much would you have to take so that you could just keep sliding this over and get the pattern? Would you need the whole thing, all 4 of them? No. What would you really need to make the entire pattern? Just one of those upside down V's, right? So we call this the period, because this can be moved over and get you this part of the drawing, and this part of the drawing, and this part of the drawing. So it's like the smallest bit you could cut and paste that would give you the whole process. That's what a period is. So what we're going to learn is, how do you find this number and this number in order to tell us from here to here is one period of that graph? And we're going to do it with the trig functions. And then we're going to start our work on the unit circle. And it's the big unit circle that's right outside my door out there. And again, some people will say memorize it. To me, there's not a whole lot of memorizing that goes on there if you know your 30, 60, 90, and your 45, 45, 90 triangles. So trigonometric functions of any angle. What we're going to be looking at is there's an initial side, there's a terminal side, there's an angle that's formed in between those two. Notice this isn't set up so that it would have our perfect initial side on that positive x-axis. That doesn't mean we can't do it. It just means that real world, we're not always going to be able to line everything up perfect with our x-axis. So what we want to do is identify the following correct geometry notation so that when we talk about this stuff later, if you're having a problem with a particular portion of it, you'll be able to tell me what portion it is. For instance, the initial side. The initial side of an angle is a ray, and so is the terminal side. They are both rays, and they are joined at a spot called the vertex. So the initial side here would be ray BC, because the ray starts at B and then continues on in the direction of C forever. That's what notation for ray tells us. It's kind of like a line with a missing arrow, you know, because we're saying it's starting here and it's going to the ray forever. Now our vertex is where those two rays meet, and that's down here at B. What would our terminal side be? Is it another ray? What are the initials for the ray? BA. We want to start here and go there forever. Ray BA. So made up of two rays that meet at a point, and that point is called the vertex. The blank is a number that describes the amount of rotation from the initial side to the terminal side of the angle. That's going to be the measure of the angle. Could be in degrees, could be in radians. Something we're going to need. If we want to do some calculations and tell them something about what's going on, the measure of the angle is a number that describes the amount of rotation from the initial side to the terminal side of the angle. Positive rotations, we already have talked about this. Like I said, this is not new material here. Counterclockwise. Negative rotations, clockwise. So far, our review. Some geometry review, some trig review. Now the angle we saw up there was not lined up with that positive x-axis for that initial side. And that's because it wasn't in this form, which is standard position. We like standard position because most of the math that we do becomes easier if we're using 0, 0 as that vertex and lining things up nicely. That gives us a really good visual. That always makes trig easier too. So it involves the placement of an angle on the xy plane so that the initial side is located on the positive x-axis. The vertex is the origin, and then your terminal side describes where your angle should land. So this one, they're showing us with the arrow that this is going to be counterclockwise, which would mean this is a positive angle. If you had to take a guess, what would you say for the degrees for this angle? Nobody wants to guess.
Can you repeat the question?
If you had to guess, what would you give me for a measure in degrees of this angle? Something along those lines, huh? Just kind of like that. This one, negative clockwise. Look at where this one's going. What do you think? Negative 190? Negative 200? Something in there. Without a protractor way to measure it, we'd see, yeah, that's pretty good. So two angles in standard position where A is a counterclockwise rotation that gives us a positive measure in this term. They have this labeled alpha. And then over here we have a beta, which would give us a negative clockwise angle. So down here it says, how could two different angles have the same initial side and terminal side? What's that called? What's the fancy name again? It lands in the same place. Coterminal. Good. Coterminal. Would their angle measures be the same? No, we had to add and subtract 360. We had to add and subtract 2 pi from that. So no, not the same. They won't be. But they land in the same place. And that's important because what that does is it tells us that the trig for those angles would actually be the same. And there's our little coterminal again. We don't want to forget that language because that coterminal tells us if we have an angle we wouldn't necessarily want to use. Negative 2,358 degrees. Yuck. We would try to get that to the smallest positive angle that we could use. It would be coterminal with it, so all of its trig functions would be the same, but at least it wouldn't be so nasty, you know, and such a burden to work with. So, how can we find the angle measures for coterminal angles in degrees? Add and subtract 360 degrees. In radians, add and subtract 2 pi. But we of course know that usually involves fractions. You know? We're usually having to get our common denominators in order to make this work. It's just a little more work, but it's a lot more accuracy, and that's the reason that we go through all of that. So down here it says we have a set of positive and negative coterminal angles. So alpha here is a nice positive angle, but you could get the same trig functions by using beta as your angle instead with a negative degree measure or negative radian measure. And over here they're showing us two positive coterminal angles, so whatever we had for the first terminal side, we just added 360 and went around one more time to get what we needed there. Like I said, we generally want to work with the smallest positive values that we can. So down here it says the coterminal angles, we can get a positive and we can get a negative, we could have two positives. There's actually an infinite amount of coterminal angles that can be generated for any angle. So we want the nicest ones, that's what we're about. Example 1 says finding coterminal angles. Find and draw a positive angle and a negative angle that would be coterminal with the given angle. Okay, so 30 degrees. I would say 30 degrees, splitting this into threes, about there, so. There's my 30 degrees. How do I find an angle that's going to be coterminal with that? So 390 degrees. I'll just grab a different color and know that I'm going to go around and come right back to that one. 390. Are we getting the negative one? Subtracting 360. Oops, too many threes. And I'll grab a different color. Show that going in that direction, going in that positive direction, I'm still going to land at the same place. So we had to draw the positive angle and negative angle that are coterminal with this angle, and we would probably want to use a little notation. We didn't have a name for this angle, so we'll just put COT, 390, COT, negative 330. Or you could go back and label this theta and put theta coterminal for those. All right. My guess is we don't need to do B. Are we in agreement? Okay, so let's go to the radians one. We have this 2 pi over 3. So the first thing we'll do is we'll get the visual. How are we supposed to think of it again when we do the visual? 2/3 pi. All right, so we're not going to go all the way across 1 pi. We're going to go 2/3 of the way. And this time I'll label that theta. So now we need positive and a negative coterminal angle to 2 pi over 3. So what should we do? Add 2 pi. And there's the problem, because we need a common denominator. So we're going to have to multiply by 3 on the top and the bottom of this one. So we'll really have 2 pi plus 6 pi, which would give us 8 pi over 3. But the drawing's not tough, because we know what we just did. We just added a rotation. So we go back and say, okay, we started here, but this time we went around and came back to that terminal side. All right, they also said we need a negative. What do we do to get that? So we'll subtract 6 pi over 3 and get negative 4 pi over 3. And that one will be represented by my green right there. And this time, since we had, like I said, I put a theta in the middle there. For notation, we would want to do theta coterminal, 8 pi over 3. And then I could probably just use a comma to separate it. And negative 4 pi over 3. Because that's the way your book kind of things is just kind of listing them out in a row. All right, so that's stuff we've been doing. Just finding those coterminal angles. Now, like it says, we need to extend our trig functions so they apply to any angle. And we start in the first quadrant because everything is positive in the first quadrant. And the quadrants are counterclockwise, just like the angles. So quadrant 1, 2, 3, and 4. And you do need to use Roman numerals for those. And that's because historically Roman numerals have always been used. Math is big on history, so we try to keep that. So like it says, the 4 quadrants, both x and y are positive in quadrant 1. We would love to work there whenever we can. But quadrants, like it says, like superbowls, are invariably designated by Roman numerals. So we always use Roman numerals for those quadrants. Investigating first quadrant trigonometry. It says let P be a point xy, any point in the first quadrant, and let R be the distance from P to the origin. I need a visual of that. Bless you. just like so. I put the point on there. That's what they wanted me to do. Now it says, R is the distance from P to the origin. So stop and think. Well, if this is X and Y, I can make a little triangle, a right triangle in fact, that has X and Y as its two sides, and then it has R as its hypotenuse. So, using this, it says, use the acute angle definition of the sine function to prove that the sine of theta equals y over r. Okay, the sine of theta is, what's our definition? Opposite over hypotenuse. So what they're saying is, this little angle right here at the origin that's formed is going to give us what we need. So we need opposite over hypotenuse. That's going to be y over r. And then it says we want to express cosine theta. We do that the same way and say, hey, cosine, that's adjacent over hypotenuse. So adjacent over hypotenuse would be x over r. Tangent. All right, well, that's opposite over adjacent. So that's going to be y over x. And then it says, what about the other three? Well, we know those are just reciprocals. So the reciprocal of sine is going to be cosecant. And the reciprocal for cosine is secant. And the reciprocal for tangent is going to be cotangent. So we just flip them. If sine is y over r, then cosecant is r over y. If cosine is x over r, then we'd have r over x for secant. And tangent was y over x, so cotangent is x over y. Well, that's a big waste of time. We already knew all that stuff. Well, except for the x and y and the r stuff. And that's because this is called coordinate trigonometry. It's a way to do the trigonometry without having to make a picture, is what this is. I'm a picture person myself. You know, I draw the pictures. It puts it all together for me. But they're saying, you know what, if they gave you the point, you could figure out what r is, because this is a right triangle. So if you needed to know r, you could say, well, x squared plus y squared equals r squared. So the square root of x squared plus y squared is going to give me r. And technically, you wouldn't need to draw a picture, you know, because you'd know, hey, they gave me the point. Here's x and y. I can use x and y to find r, and I can use coordinate trig to get what I need. Y over r, x over r, y over x, etc. So coordinate trig can be helpful too, but you definitely can do it visually. So this says, let's let theta be an acute angle in standard position whose terminal side contains the point 5, 3. Find the 6 trigonometric functions of theta. I told you before, I don't do anything without a picture when I'm talking about trig. I just don't. I want it all to make sense visually. So I think about where a 5, 3 might be at. Draw my triangle and realize, well, this is the 5 and this is the 3. And if they want the 6 trig functions, all I have to do is Pythagorean theorem to get r, plug them in, y over r, x over r, y over x, and see what I get. So this is a good spot for me to have you get started on that and get your candy partner. And see that everybody's getting this before we move on to anything tougher. Remember, we always rationalize the denominator. Yeah, if you make the picture, technically you don't have to memorize y over r, x over r, and y over x. You can just use the picture and use opposite, adjacent, and hypotenuse. Yeah, you're welcome. All right, so I do know some of you are still working on it. That's okay. Let's get with the partner in case somebody's struggling a little bit. We're gonna help them out. So candy up in the air. Make eye contact with that candy partner and find a spot where you can sit next to each other. Don't forget to introduce yourself. You haven't been together that long, so. If you can't find your partner, come to the front of the room. They'll probably meet you here.
Oh, sorry.
Where's the other dum-dum sucker? Hard work, and they have their head down.
Or they just don't want to be with me.
Oh.
That would not be cool.
It's fine.
Well, join whatever they want. If they want an antisocial, then that's just their loss. Oh, you know. Oh, or we might have another day with two people that were gone.
Oh,
You're right.
okay. You can be with us. Alright, I did it right, but then I forgot to find square. So, yeah. So then it's the sign would be 3 times the square root of 34 over 34. Yeah.
Sine of theta, what'd you get? Kind of nasty to rationalize the denominator of the square root of 34, right? Yeah, but we get used to it. Cosine, what do you got? Well, it's good to know one person knows these. What do you got? 5 squared root of 34 over 34. How about tangent? A little bit easier for the bottom three, right? Cosecant, what was that? Square root of 34 over? How about secant? Cotangent. A really nice one, right? There we go. So we have this radical, and after you do a few of these, you realize, okay, I've got 3 over the square root of 34. But every time I rationalize the denominator, all that happens is I move this up here, and then I write it down here without the radical on it. Yup, every time. Every once in a while, there'll be something that we can cancel, but that's once in a great while. So when you see this, it becomes automatic to say, okay, that's going to be 3 squared root of 34 over 34. And it's not such a burden anymore to do all the math as you go through it. So we've got this in standard position, but it really wasn't given to us as an angle. It was given to us as a point, and that's what makes it coordinate geometry. Now, You can learn, like I said, y over r, x over r, y over x for the primary trig functions and just flip those over. But you can also draw a picture, and that makes it easy to do as well. So it says use the same definitions for x, y, and r whether or not x and y are positive. So it doesn't matter what quadrant we're talking about here. And you can extend the trigonometric functions to any angle. Okay, but what if they give me a point out here? How am I supposed to get my triangle? You use the reference triangle. The reference triangle is always the triangle that's formed with the closest x-axis. And that's what we do. So, question is, why will r always be positive? Tell your partner, why is r always going to be positive?
Yeah.
Two overall reasons. Some of you are talking about it in terms of the formula. You're saying, well, when you put it in the Pythagorean theorem, you're going to square both numbers, and when you take the square root, it's going to be positive. The other is, it's a distance. That's what it is. It's the distance from the vertex to your point. Distances are always positive. Now that doesn't mean your Pythagorean theorem explanation that I heard lots of people using out there is wrong. It doesn't. But just to break it down into something really basic, it's a distance, and distances are always positive. So that's the reason that r will never be negative. So evaluating trig functions determined by a point not in quadrant 1. Well, now we have negative 5, 3. You and your partner. Negative 5, 3, whether or not you want to use the coordinate trig with y over r, x over r, and y over x, or if you're a visual person like me and you want to draw it.
And then you say,
No.
stuff is the box.
Got it? Yeah. Yep. One of the reasons I wish we had more time for candy partners and that kind of stuff in pre-calculus is the great conversations that I could eavesdrop on. And people were immediately talking about shortcuts to this. And so then the conversation became, well, it's still a 5 and a 3, so the number part's going to be the same. It's just the negative that we need to worry about. And then it was, well, the negative of what? You know, which of these would be affected, which ones would be the negative? Well, any of them that have x in their computation, because x is what's negative in this case. So you go back to sign and you look at the example we just did, and you said, well, it was 3 square roots of 34 over 34. And you think, does that use x? Well, the opposite side is always the y. And r doesn't have a positive or negative value. Hey, we can just use the same one we had for sine. And then we go over here and say, well, this one was the square root of 34. That doesn't look like a square root. Over 3. And then flip that over to do the sine piece there where we rationalize the denominator. Then we go down to cosine. And the numbers were the same, so 5 square roots of 34 over 34. Does cosine use the x? Yes, it does, because that's the adjacent side. So this one would have to be negative now. had for secant, obviously, since that's the reciprocal, would also now be negative. Tangent, numerical part of our answer was 3/5. Does tangent get a negative? Opposite over adjacent again. There's our adjacent. And that also means that cotangent will be as well. So it's, like I said, those conversations that help you do things a little bit faster, because when you do your homework and you see, oh man, this one says use 0.23 and this one says use -23. You have to do all that again? No. If you recognize that, then use that knowledge to go where you need to. So there are an infinite number of coterminal angles that are going to share the 6 trig functions above, because anytime we land in that same spot, we're going to have the same trig functions. It's going to work that way. So use those shortcuts if you see them along the way. Next page says trigonometric functions of any angle. And we should not be shocked to see all the stuff that we've just talked about right here. Y over R, X over R, Y over X. But then they have this little disclaimer, which by now we're used to. Tell your partner why we have to have those little disclaimers. Have to restrict the domain because we can't divide by 0. That's what they're saying here. And that's that domain restriction that we see right there. So the 6 trig functions, you can always make a draw. You can always make a draw. That way you wouldn't have to memorize all this stuff. But bless you, when some people are doing a lot of coordinate trig, then yeah, do you want to memorize Y over R, X over R, Y over X? Yes, if you're doing lots of it. It'll just happen by accident. So that's up to you. I like the drawings. What happens when we're not given a point to begin with? Oops. Well, we're going to have to work our way backwards to finding one. So we'll work backwards to find one. Well, how are we going to do that? We don't have a lot of experience with every angle that's out there. No. So we should be suspicious that they might be 30 degree, they might be 60 degree, and they might be 45-degree angles. Because those are the ones we've had a lot of experience with. Those are the ones we should recognize when we see them. So this one says we're going to evaluate the trig functions of 315 degrees. And we're not using a calculator. We're not. We're going to make a drawing. And we're going to see what is it about 315 that's so special. That's something we should already know. So let's see. Starting there, we're going 270. And then we'd have to go a little bit more. How much more? And the light bulb comes on and we say, oh, look at that. If I draw this triangle right here, this is going to be a 45, 45, 90 triangle. And I know what's supposed to go on 45, 45, 90s. 1, 1, square root of 2. Except I'm not in quadrant 1. We need a negative every now and then. Which of these needs the negative? Down, negative 1. So we could say, hey, this is the point 1, negative 1, and we could use coordinate trig, or we've already got the thing drawn. We could just use SOHCAHTOA for whatever it is they want us to find. So sine of 315 degrees, cosine of 315 degrees, tangent of 315 degrees. Notice we don't use theta anymore because we know what we're supposed to evaluate. And then we'll do cosecant of 315, secant of 315, and cotangent of 315 degrees. Like I said, if you want to use the coordinate trig, absolutely, go ahead and do that. But right here at the vertex, I see my 45 degrees. And I think opposite over hypotenuse, negative 1 over the square root of 2. And in my head, I multiply the top, square root of 2. The bottom will now be a 2. So negative square root of 2 over 2. You don't have to do it in your head either. You can write all that stuff down. Cosine of 315 degrees. Well, that's going to be adjacent over hypotenuse. 1 over the square root of 2. And you realize, well, I just did the math for that. It just doesn't have a negative on it. So that'll be the square root of 2 over 2. Tangent, opposite over adjacent, like that math. -1 over 1. Makes cotangent nice and easy too. Then we go back and think, okay, how did we get what we had for cosecant? Well, usually I'll just start over and say, well, sine was opposite over hypotenuse. This is going to be hypotenuse over opposite. Square root of 2 over -1. That's the negative square root of 2. Secant you get from flipping cosine, and cosine is adjacent over hypotenuse, so hypotenuse over adjacent, square root of 2 over 1. They have to give us angles we're familiar with. Something that we could use, and that means that our reference angles are going to end up being something nice. They have to, because those are the ones we have experience with. So that drawing piece, incredibly important. Find where the angle is, drop that right triangle, and see if you can figure out what you have to work with. Now, these are the steps. You draw the angle theta in standard position, carefully placing that terminal side in the correct quadrant, because that's the piece that people forget. You know, if something's negative, I've got to make sure I have that on there. Without declaring a scale on either axis, label a point P other than the origin on the terminal side. Yeah, I didn't put any 1, 2, 3, 4, 5 on intervals or anything like that. I was just looking at what do I have for my angle. So you draw that perpendicular segment from P to the x-axis because the x-axis creates that reference triangle. If this triangle is one of the triangles whose ratios you know, you better be given those answers exact. Label those sides accordingly. If it's not, then we don't have a choice. Then we have to use the calculator. I'm telling you, if you're using a calculator for this section, for any of them, you're probably making a mistake, because you should be able to find those 30, 60, and 45-degree angles. Use the sides of the triangle to determine the coordinates of P, making them positive or negative according to the signs of X and Y in that quadrant, and then use those coordinates and the definitions to determine the 6 trig functions. This is where I would go away from the book and I would say, I'm going to use my picture. I already have it drawn. What do I need to know the coordinate stuff for? Because we wouldn't need it. So down here, it says evaluating more trig functions. Now, again, we're going to do these without the use of a calculator. So, 4, 3, 2, 1, 0. How do you feel? Do you think with your partner you could rip these out, or should we do some of these together yet? We're going to do some together yet. There's a couple numbers out there that make me feel like somebody's not quite comfortable with this yet. All right, negative 210. What's that supposed to tell me? Clockwise. All right, so clockwise, there's 180, and I have to go a little more. How much little more? 30. Oh, and we just told ourselves what kind of triangle we're going to have here. Yeah, that's not readable. I will draw an arrow. It's 30 degrees. So remember, in that 30-degree, 30, 60, 90 triangle, the 30-degree angle is always opposite the shortest side, because it's the shortest angle. And that's always a 1. So that's going to be a 1 piece there. And then our hypotenuse is always twice as big as that side, so the hypotenuse is 2. And then the other side is the square root of 3 from the song. So that's what we have. But it's not in quadrant 1, so everything can't be positive. Which one of those is going to need a negative? Square root of 3. So if we wanted to, we could write this as negative square root of 3, 1, and that would represent that point up there. If they asked us, if they made us do that, we could do that. But really, we could just use our SOHCAHTOA piece here. So we are really looking at the side of negative 210 degrees, but we are using our reference triangle of 30, 60, 90 to get there. They didn't ask us for our reference. They asked us for negative 210 degrees. So sine of negative 210. How do you find sine? Opposite over hypotenuse. Hey, that's one hand. Love that. How do you find cosine? Adjacent over hypotenuse, so negative square root of 3 over 2. Ooh, that one was quick as well. How do you find tangent? Definition of tangent. Opposite over adjacent. Oh, little work here, because we've got 1 over negative square root of 3. Again, you can visualize bringing the square root of 3 up and making this a 3 on the bottom. Then we have to do the secondaries. Oh, they didn't even want them all.
Yeah.
Oh, look at that. Should we do the rest?
No.
You're good now? Okay. The radians one, huh? Tell me how you're going to think through where that terminal side is. 5/3 pi. Okay, 5/3. That's actually 1 and 2/3 pi. So we need 1 pi, and we have to go 2/3 of the way. Thirds.
60 degrees.
180 is pi. So if we take pi and we're dividing it, and there's a 3 on the bottom, it has to be 60 degrees. There's our reference angle right there. So that's not the small one. The small one is the 30 down here, and that has the 1 that's going to be opposite the 30 degrees. Our hypotenuse is going to be 2, and we get the square root of 3 opposite that 60-degree angle. So again, we could give them a point, but what's really important here is knowing which of these gets a negative if one of them gets a negative. Which one is it? Yep. We're going out 1 in the positive direction, but down. So this would be 1 negative square root of 3 if you wanted to do the coordinate geometry. And this time I will notice they only want tangent. So the tangent of 5 pi over 3. They didn't ask us what the tangent of 60 degrees was. They said, what's the tangent of 5 pi over 3? The good thing for us is, it is the tangent of 60 degrees. So what do you get for the tangent of 60 degrees? Negative square root of 3. Opposite over adjacent. So now, even though there are a couple of low numbers, your partner didn't have a low number. So I'm going to have you give the secant of negative 3 pi over 4 a try with your partner. I didn't get over here, but what's your reference angle from the center? Reference angle? 45 degrees. Yeah. Pi over 4 because we have a 4 on the bottom here. And 180 divided by 4 would be 45. There's your reference triangle. One of them needs a negative? Both of them need a negative? I mean, we know the hypotenuse doesn't need one. One or both? Left and down. secant. Tell your partner what you flip to get secant. Okay, so cosine is adjacent over hypotenuse, which would mean this has to be hypotenuse over adjacent. Square root of 2 over negative 1. I better write it out in steps for people that aren't here. I keep wanting to slap the negative up there right away. So that is our secant of negative 3 pi over 4. There we have it. So reference angles, reference triangles, huge. Now, angles whose terminal sides lie along one of the coordinate
Sarah, we'll get out in
axes.
2 minutes.
Okay. Thank you, Sai.
Cedar Home.
I love this stuff. I would have ended up just ranting all the way till the bell anyway. So, quadrantal angles. That's a good place for us to stop because with quadrantal angles, we do want the coordinate geometry memorized. Bad news. You probably won't be able to do all of these. I know, it's a bummer. I'll make it up to you. We'll catch up tomorrow and go forth from there. But do what you can on this because we have it covered quite a bit. We just didn't get the quadrantals yet. Feel free to take a picture if you have to go. Otherwise, I will put this on the completed notes on school. I don't want anybody late.